welcome to today's class in at Gaussian elimination as an introduction to solutions to systems of linear equation using numerical approach. So what we are saying today is given any system of equation, okay, of any dimension, in the lower stages we looked at 2x2 systems and 3x3 systems. That's equations, 3 equations with 3 unknowns. That makes up a 3x3 system, right? Here we are looking at a system of any dimension because real life systems go beyond 3x3, 4x4 systems of equation. So we are saying that if we have a matrix or a system of equations of n equations with size m, okay, that we are supposed to solve for it, how do we go about it? Now the challenge here is the bigger the matrix, the more difficult analytical techniques become. And also we all know that analytic methods become let's say more involving and time consuming, okay, as the system increases. And in real practical sense, if you're looking for a solution, a exact solution to a system, and you have to spend like 5-10 minutes in a critical condition, then it becomes a challenge. Hence the need for an iterative, or let me say a numerical approach, okay, where we allow the computer to do the solution, to find the solution of the system for us by just a click of a button, and you have your answer. Now, Gaussian elimination is an approach which is used to get the solutions to any given dimension of equation. Okay, so it says in these equations, if we are given aij, where ai's are the coefficients of x and bi's are the solution, okay, that's any given real numbers. We can write them in the form ax is equals to b. That's the general form, okay, where A is the coefficient matrix whose element in the ith row and jth column is aij, and then B is the column vector or the solution matrix whose ith entry is bi. This gives us an easier way of representing the equation as what? A11, A12, A13 to A1n, then you write the corresponding rows. So it goes aij, where I are the elements in the row, and j is the column of the matrix. So for example, A21 is the element in the second row, first column. A22 is element in second row, second column. Now, the task in Gaussian elimination is first to reduce the augmented matrix to an upper triangular matrix, and then 2, to solve the resulting matrix using a backward substitution approach. Now, this is what we mean by an augmented matrix being transformed to upper triangular matrix. So in this case, if we're given, for example, a 3x3 matrix like this, and we write it in the form A, X, B, okay, then we're going to transform all the elements under the leading diagonal here, where you see the line. Okay, so this value should go to 0. This should also go to 0, okay, and then this will also go to 0, like we can see over here. Okay, so all the elements below the diagonal should go towards 0. But how do you do that? You can use the elements in the first row, that's A11, to reduce the elements in what? A21, and then the element in what? A31. Then subsequently, you can use the next row also to reduce the element in what? A3, 2. Okay. Then when you're done, you rewrite the matrix like this. This is not an exact demonstration of what we get, but what we are seeing here, we can rewrite the equation maybe as what? 1x plus 5y plus 7 is equals to this, and minus 3y minus 4 or plus 4z is equals to negative 36, and then minus 2 is equals to this. It's not exact, but that is the form we'll get, and then you use a backward substitution to find your x, y, and z. Okay, now these are some operations, or these are the general steps in Gaussian relation. Like I said, first you have to reduce the augmented matrix to an upper triangular form. Then secondly, we apply row operations. There are 3 operations that we can apply. Okay, and these iterations must be clearly stated. All operations used in reducing the matrix should be clearly indicated at the proper place. And like I said, there are 3 main operations. We can multiply a row by a non-zero constant, and then we can also add a multiple of another row to a given row, okay, to reduce it. Or we can swap to, so like you can see, this is the case where we are adding a non-zero constant of row 1, okay, to row 2 by subtraction. Then step 3, you have to solve the resulting matrix using the backward substitution.
Yeah. So we